Um, the original title actually is a little bit smaller than than what I want to discuss today. So uh, here's a better working title for it. I want to talk about work that's been done in the last year or so to integrate NSCL SpecTcl and SQLite 3. Um, the outline of the talk is as follows. So I've talked here before, and I've given some information about the National Superconducting Cyclotron Lab and the Facility for Rare Isotope Beams, but I'll do a quick overview of what it is we do, what we study, and what experimental data comes from. I want to then talk a little bit about what we do, uh, what data analysis looks like, what conditions steer data analysis, and then the tool that we use for data analysis, NSCL SpecTcl. Then after that, I'll talk about what we've done to integrate SpecTcl with SQLite. Okay, so NSCL FRIB. We are, so there's really two laboratories in one building. There's the National Superconducting Cyclotron Lab, which studies basic nuclear research using beams of unstable isotopes that don't occur in nature. Um, this is what the beamline plan looks like. There's a pair of cyclotrons that are coupled, and then we use a thing called projectile fragmentation in this separator to produce unstable nuclei, which are transported to the experimental target. Since 2014, the Department of Energy gave us a grant to build a thing called the Facility for Rare Isotope Beams. That should come up in 2022. These two cyclotrons get replaced by a linear accelerator. That should give us higher intensity primary beams and higher energy primary beams, extending the range of experiments. This plot here is a plot of isotopes. So you have, for a given nucleus, the proton number on the y-axis, the neutron number on the x-axis. These black dots here are the isotopes that occur in nature, the stable or nearly stable isotopes. NSCL has allowed us to study the characteristics of these isotopes in the red region. FRIB will extend it to this extend our range of study to this orange region, and it's hard to see, but there's a little orange region up here on the proton-rich side as well. So we're going to be looking at mostly neutron-rich isotopes. Why bother? Well, this is a set of tables from committees that advise the funding agencies for nuclear science in the United States. The place where we mostly fit in is this blob over here. Where do the nuclei come from? Where do the elements come from? If you look at how stars work, standard series stars, you can make elements up to iron in the fusion process that lead to the end stage of a star. But where do all the heavier elements come from? And at present, we think that they come from stellar collapses that lead to supernova. So in the stellar collapse, you're getting a very rich set of free nucleons that can be captured by the nucleus and then blown out into space where they can be captured by other things like Earth. And so we're interested in how those processes work. Okay, so much for that. How do we take data? What does an experiment look like? We can't see nuclei, so we have to rely on indirect detection techniques. This picture here is one of those detectors. Detectors operate in one of two ways. Either particles go through them and they ionize the material they go through, and then an electric field allows you to collect the ions down on some set of sensors, or you excite nuclei, you excite atoms as you go through some material. The de-excitation releases light, and that light is multiplied with photomultipliers. And in the end, you just get some very small, very fast electrical signals. What we're interested in is the pulse heights of these signals, or in some cases, how much charge is in one of these pulses. And we're always interested in when these pulses happen in relation to pulses in other detectors. More recently, and I talked about this last year, we started to become interested in the characteristics of the pulse shapes themselves. And there's information we can squeeze out of digitized pulse traces. By digitized pulse traces, I mean digitization at 250 to 500 megahertz per sampling time. In addition to this raw data that we get from the detector, we also typically will need to produce some computed data. For example, a detector like this, the target's going to sit in the center of it. We might want to know what is the angle between two hits in that detector. We might want to know time differences. That's really what's important, more important than time. And for the cases where we're taking traces, we might want to actually fit that trace data and get some information out of those traces. So that's what the raw data looks like. What we produce from this is a thing called just some histograms. We call them spectra for historical reasons. Over to the left are a set of a couple spectra from an experiment run by Alexandra Gada at the NSCL. I want to just draw attention to a couple features. One is you see there's a red circle around this blob here and is identified as 36 magnesium. So that's magnesium 36. It's one of the isotopes of magnesium. This spectrum, time of flight on the x-axis and energy loss on the y-axis, gives you isotope resolution. So each of these rows is an element, and each of these columns is an isotope within the element. So this is 36 magnesium, 37 magnesium, and so on and so forth. At the bottom, the thing I want to also draw your attention to is this x-axis is not a raw x-axis. It's a computed parameter. It's an energy calibrated value. And furthermore, the last thing I want to say is this spectrum here was generated by restricting its increments to events that live inside of this 36 magnesium blob. So this is the energy spectrum of 36 magnesium, and as opposed to 37 magnesium or a soup of different isotopes. This kind of gating, this kind of creating conditions and applying them to spectra, gating spectra on them is an important part of data analysis that we do. What often happens is we have a data set that may consist of several terabytes of raw data, and we're going to go over that data set over and over and over again with different analysis conditions. Someone might ask Alexandra, yeah, but what about the energy spectrum of 36 magnesium? And then she'll draw the gate around this thing and refine it until it looks right to her and look at that spectrum again. So that's very important when we talk about putting event data into SQLite. I first talked about NSCL SpecTcl back in 2004 in New Orleans. So it's been around a while. It's our basic tool for generating histograms. It's got a bunch of windows. I'm not going to talk a lot about them. The main thing is it's very interactive. It's an extended TclTK script. It now has interfaces with one of the standard tools in nuclear and high energy physics, CERN's root. How does it work? What does it do? Well, it's a framework that the experimenter has to write some code to use. What the experimenter has to do is take this raw event here and transform it into parameters that are recognizable by the rest of SpecTcl. And then SpecTcl can produce whatever histograms you want from those parameters, from the event parameters you've extracted from that event. So the user has to produce a thing called an event processor, at least one of them, and that maps data in this raw event, decodes it, and produces parameters. Now, in fact, you can have a pipeline of these event processors. Each pipeline element has access to the raw event and the parameters produced by previous elements of the pipeline. This allows subsequent event processors to become more and more loosely decoupled from the raw data. For example, that the computation of the calibrated energy doesn't need to know anything about the raw event. It just needs to know the parameters it's operating on. The event processing pipeline also allows us to glue together several detector systems into an experiment, and that's done routinely. So you could have an event processor for detector 1, event processor for detector 2. They look for their data in this raw event. They produce their parameters in here. Neither of them has to know what the other one is doing. So again, we wind up with the concept of event processing pipeline. Two more architectural slides, and then we'll go on to maybe the good stuff. So this is one way to look at SpecTcl's architecture. There's an event processing pipeline. It produces an array-like object of parameters. These parameter definitions define which slot in this array-like object a parameter lives in. There's a histogramming engine that's been very highly optimized. It takes spectrum definitions. A spectrum definition requires a parameter definition, gate definitions, which can result in conditions on these spectra, and then it produces a bunch of, for each of these events, it decides which spectra to increment and where. And then there's a decoupled visualization component. So all the stuff inside this box here, those are the analysis, those are what I'm going to call analysis conditions. These are the things that typically a user will change from run to run over raw data. It's important to note that this is not in the event processing pipeline. But on the other hand, and here's another way to look at this, what SpecTcl does, all of the processing time, pretty much all of the processing time in SpecTcl lives in this event processing pipeline. That's where all the complicated work does. That's where all the unoptimized code lives because we don't write it. That's where the compute time lives. So last year I talked about some things that we did to improve SpecTcl performance. There's a couple of things we did. We can parallelize it. We did that. Giordano, my colleague, built a threaded version of SpecTcl. The key point is that since events are samples from some probability distribution of possible outcomes, each event can be processed independently of every other event. So you can trivially parallelize this event processing pipeline, pull together the decoded events, and then histogram the results. That worked out quite well. We got performance on a very simple case up to the IO limited performance of a local solid state disk. That's 3 gigabytes per second in this picture. But on the other hand, if we're running over these events over and over again with slightly different analysis conditions, why are we bothering to do that? Why don't we just save the results of the decoded data and use that for subsequent replays of the analysis? So that's kind of the motivation of this work. One is saving and restoring analysis conditions and the results of analysis, and then also saving the output of the event processing pipeline so that we can replay it without needing to invoke this pipeline over and over and over again. By analysis conditions, again, I'm going to define these as parameter definitions and metadata. By metadata, I mean suggested ranges for histograms, suggested binning, resolution of the parameter, and the units of measure of the parameter. Spectrum definitions, again, what parameters are used to increment the spectrum and how the spectrum is incremented. SpecTcl has a very rich set of histogram types to meet the needs of these parameters. Gate definitions and their applications to spectra, and then steering variables. And by steering variables, I mean, if you're doing an energy calibration, calibrated energy computation, for example, that computation often has a set of calibration values, and these steering variables capture those values. Okay, so we chose to use SQLite to store this stuff. Why? Well, one reason is that there's this conference coming up, and it was cool. It'd be cool to have a paper in it. But I think most of the reasons in this slide are reasons that pretty much everyone here uses for choosing SQLite over, say, MySQL or PostgreSQL or what have you, whatever SQL. For us, what is also attractive is this large capacity will allow us to store the entire experimental data set in these databases for moderately sized experiments, and so on. Okay, and again, all this is there. So let's look at what we did. We wanted to have a single database instance, a single file, store many different analysis configurations and many different runs of many different data, so that instead of having this soup of files that people currently have, there's analysis condition files over here, event data over here, spectra over there. Instead of having that soup of files in all different places, we can pull together everything they need into a single file that describes the experiment and tracks what people do in it. So we do that by dividing the data into save sets. A save set is just a name thing and a timestamp that says when you built it. And then typical database stuff, everything that you've got, for example, parameter def has a foreign key that points you back at the save set it belongs to. Everything lives in a save set either directly or indirectly. And I'll give an indirect example when we get to the event data, and so on and so forth. So all of our definitions kind of look like this. They all have a save set ID of some sort. Spectrum contents, those are pretty easy. Each spectrum you can think of as a one-dimensional or a two-dimensional spectrum. Here's a top record of here's a root record definition of a spectrum. There are sub-tables that point back to this that I'm not going to go into, that define, for example, axes and the parameters it needs and so on. Note that it has a save set ID, so this spectrum definition lives in a save set, has a name and a type. The type determines how this spectrum is incremented. And then the spectrum contents just has an ID that's a foreign key back to the spectrum ID in this case, a mandatory X bin and an optional Y bin. They're a one-dimensional spectra. They'll only have X coordinates, and two-dimensional spectra will have Y coordinates as well. And then the value of the bin in that spectrum. We only store the non-zero channels, both for performance and to keep the database, that chunk of the database relatively small. Spectra can be large. They can be 4,000 by 4,000 channels or even larger. Some of the digitizers we have now generate 14 bits worth of resolution. So spectra can be big. Okay. We chose not to make the spectrum type a data type, something that's looked up from another lookup table. Validity is enforced by the API in SpecTcl, and we wanted to be able to allow the set of spectra to change without having to affect anybody's existing databases. All right, so let's look at how we might store event data in here. It looks like I'm going to get us well back on track for time. Event data comes and runs, as I said when I was talking about the logbook application we're working on. Runs have run numbers, titles, start times, and stop times. So that's a pretty simple simple table definition. Our first try was to say, well, let's do an ordinary database definition-y kind of way to make an event, to describe an event. Events have several things that are parameter IDs, the slot in that array-like object, and values. So we could define an event like this. There's some ID, which is just hanging a primary key on it. There's a foreign key back to the run number, the run ID, and then there's an event number within the run, and then parameter numbers and parameter values. And this works. It works, but playback performance is really, really bad. And it's bad especially for simple event processing pipelines. It's bad because for a given event, we've got to pull several elements out of the result set, and we've got to glue them together in an event. We have to notice when event numbers change and all that kind of stuff. So let's look at the second try. So this is fine. How we define a run, fine, no problem. What we did basically was put the data for a single event inside of one row of the table in a blob. So what we did is we said, we added this parameter count field, the number of parameters that have been assigned a value by the event processing pipeline. Events are sparse. If you look at the detector, that Sega detector in one of the early slides, in any given event, maybe only 2 or 3 of those detectors might have a hit in them. And then we put an event data in this blob, and this blob is just contains an array of structures that look like this: the parameter number and the parameter value. So what we've done is compress the multiple rows that were required to describe an event into a single row. And hurrah, that worked very well for all of the event processing pipelines we've tried it on. Even the simplest one, the simplest event processing pipelines we've tried it on, we get at least a factor of 2 performance gain. For more complicated, I can't give you our speed up is a factor of X, because the speed up depends on the event processing pipeline and its complexity. Okay, so what does the programmer see to this, and what does the user see? The the programmer sees a very low level API in C++. It understands how to save objects into this database, not write rows and columns, but objects and how they relate. There are TCL bindings. SpecTcl is an extended TCL interpreter. And I should say that initially I did this thing, I did this beast as a pure TCL or nearly pure TCL prototype, but I had a guy say, gee, I need some Python bindings to be able to use this thing in my area, in my program. So I hoisted those raw TCL bindings down, those raw TCL interfaces down into C++, re-implemented TCL bindings on top of them, and then did Python bindings for him. Why? He needed them. Newer students that are coming into our lab generally know Python, so we can cater to them to export data from this into their own custom stuff. And also, as I indicated in the talk on the logbook, we may want to in the future, in fact, we probably will want to in the future, interface our data with Jupyter notebooks. And while there are TCL, as was pointed out to me, there is a TCL interface to Jupyter, Python is still the natural language for programming Jupyter in. The GUI front end there's a GUI front end that users of SpecTcl see. Before I show this, I'm going to first put a disclaimer out. The picture here I realized is something I stole from a very early pre-release. So there's going to be mistakes in this. In particular, squint a lot when you look at the dates and times because they're wrong. This is what the interface looks like. Oh, gee, everything is January 1st, 1970. Yeah, squint at that, ignore it. This is just a tree view. Each save set looks like a folder. So there's a save set. This, in the current versions, is the actual time that the save set was created rather than epoch. This analysis conditions are considered to be inseparable, atomic. So this blue blob here is the set of analysis conditions that were saved in the save set, that define what is going on in the save set. In addition, we saved 4 spectra. These things that look like histograms are spectra. This last thing here that looks a little bit like a steering wheel to people who are young, but to us older people, it looks maybe like a reel of magnetic tape. That's event data that's been run through the event processing pipeline for this run 3, and a run with a title called my run title. So using this GUI, you can say, look, I'm about to analyze a run. I want you to load the event processing pipeline into this save set, into this, and then you can also say at a later time, I'm going to modify some of my gates. I'm going to modify some of the conditions. I want you to replay that run with these new modified conditions. So that's the gist of what I wanted to talk to you about today. Sorry, I'm getting ahead of myself. Finally, this is really early days for adoption. So we're in the point where we're getting user feedback, people using it and deciding what they like about it, whether they like it, what they don't like about it. That will inform our next release of this. And while this was all very heavily unit tested, as usual, we need some users to beat on it so that we can find out what those last defects are and get them beat down. Sticking all of this stuff into one database file is a better organizational tool for the people who are using this. It also allows them to pass that stuff around to their collaborators. I don't envision multiple users writing to this database. I envision this as something where somebody will hand that file off to somebody and say, hey, here's how I got what I did. And then we also get much improved performance replaying data with different analysis conditions. And with that, I will open the floor for questions. Either everybody's fallen asleep or there are no questions. Oh, here's one. No timestamp on the spectrum. That's correct. There's no timestamp on the spectrum. It's easy to add one. The thing that defines the spectrum is more the conditions under which it was created. So There is a timestamp on the save set that you can use. The actual timestamp, the actual time at which the spectrum was produced is not that important, but if one of our users disagrees with me, then we certainly can add one.